In this video, we're going to look at a really clever way to securely encrypt your communications with someone else, say over the internet. Even if the entire world knows your secret code and they can also see your encrypted messages moving backward and forward, it would still take them thousands of years to decrypt them. It's a lovely application of number theory in the real world, and it's also really useful. The RSA public key encryption method was developed in the 1970s by Ronald Rivest, A.D. Shamir, and Leonard Edelman at MIT in the United States, and used commercially around the world from the early 1980s. With just a few minor updates, like increasing the size of the key, it's still securely encrypting messages today, and hopefully will do for many years to come. Now, you could agree to use a particular secret code with a friend. For example, something like a simple Caesar shift cipher, in which every letter of the alphabet is shifted a certain number of places before sending the message. There are a few problems with this, though. For example, on average, we use various letters in different frequencies in our messages. In English, we use the letter E most frequently, and the letters T, A, O, I, and N the next most frequently. So an interloper could look at the relative frequencies of the letters in the shifted message and make a pretty good guess at how many spaces the alphabet had been shifted, and decrypt the message. Also, with only 26 letters in the alphabet, there are only 25 different shifts that you can use. Shifting 26 places would loop each letter right back to itself, which wouldn't make for a very secret encryption method. It wouldn't take very long to try a total enumeration approach, shifting the encrypted message by 1 to 25 places and seeing which one ended up looking like readable English. But there's also an even more fundamental problem than that for widespread communication over the internet. If you hadn't met up offline and agreed between you in secret how many places you'd shift your letters, then you'd have to communicate that number online. But how would you do that in a secure but unencrypted way? Tricky. In fact, most communication on the internet is like this. You're talking to people in other countries or businesses or banks, and it'd be impractical to pop round to see them and agree on a secret key to use for your online communications. There are far more sophisticated encryption techniques than the Caesar shift cipher that you could use, but still most of them require some sort of a key, which you'd need to communicate with the other party in an unencrypted way, and anyone trying to decrypt your message will be able to intercept the key and unlock your encryption. So what we're going to look at is a thing called public key encryption, and it's a cunning method that effectively bypasses the problems that we've just talked about. Now, you might be surprised to know that the method of encryption is published in detail and available to everyone. So in theory, when you use it, anyone can reverse the method and decrypt your message. The cunning part is that while it's easy to encrypt a message using this method with the public key, working backwards is much, much harder and would take even the most powerful supercomputers many, many years to work out without the secret key that only the receiver knows. The public key encryption algorithm is a series of mathematical steps which we call a function. You plug a number into the function, it churns through the steps and out pops an answer, the encrypted number in our case. It turns out to be very hard to invert this function though, and to work out what went in if you know what came out. It's a bit like a cake making machine. You can pour in the ingredients at one end, flour, butter, sugar and eggs, it does its thing and out pops a cake at the other end. But even if you know exactly what went in and how it was processed, it would be very difficult to run the process backwards and turn the cake back into separate ingredients. In some cases, mathematical functions are easy to invert. For example, if the function was something simple like add 7 to the number input and output the result, then inverting it is just a matter of subtracting 7 from the output and you know what the original input was. But if the function is taking two very large prime numbers as input, multiplying them together and outputting the result, it can actually be an enormously long job to work backwards from the product and factor it out to find out what the original inputs were. And it's this principle which lies at the heart of the public key encryption algorithm. Let's go through the algorithm using small prime numbers so we can see how it works. But remember that out there in the real world, communication software on your computer will do all the hard work of generating random, very large prime numbers for you and working through the decryption process, and you won't see any of the work it's doing in these calculations. Let's call the person sending the message the sender and the person receiving the message the receiver. We're going to use simple numbers to illustrate how the process works, but your messages will most likely contain letters rather than numbers. Well, that's not a problem, because you can convert letters into numbers using their Unicode values. For example, the letter H has a Unicode value of 72 in decimal, and I has a Unicode value of 73 in decimal. If you wanted to send the message hi, you could just convert this to the number 7273, 72 for H, followed by 73 for I. Encrypt the number and send that. The receiver could decrypt the number at the other end and unpack it back to the word HI by looking up those Unicode values. In fact, because digital data is stored in binary format, those numbers would have bit settings 01001000 and 01001001 in bytes on your computer. Another way to represent these numbers is in base 16 or hexadecimal, and then they'd be 48 and 49. Now, the details of that are a story for another day, but I thought I'd mention it because if you look up Unicode values of letters in an online table, you'll probably see the binary and hexadecimal code values alongside the decimal ones, and now you'll sort of know why. The other thing is that your communication software will break your message down into small chunks because the size of the prime numbers used limits the size of the message that can be sent. By splitting the original message into a series of small messages, encrypting them and sending them individually, then putting them back together at the other end, you can actually use this method to send messages of any size. First, let's run through a very quick outline of the method, and then we'll go through an example in detail to see how it works. The receiver picks some secret private key numbers, then uses them to calculate some other numbers that they can publish to the world as public keys. Someone wanting to send a secret encrypted message to the receiver takes the public keys, applies a set of calculations to the numerical version of their message to get an encrypted numerical version, and then sends that encrypted version to the receiver. The receiver can then use their secret keys to decrypt the encrypted message relatively easily. Any hacker can see both the encrypted message and the receiver's public keys, and in theory they can use them to decrypt the message, but the encryption algorithm is very difficult to invert without the original secret keys. It would take years and years to do, even with the world's best supercomputers. Okay, so here's how it works. The receiver randomly picks two very large prime numbers, hundreds of digits long. Well, their communication software picks them. It'd be pretty hard work if you had to do that by yourself. So whenever I say the sender or the receiver, I actually mean their communication software. So prime numbers are integers, whole numbers that have exactly two factors, 1 and themselves. We'll pick very small prime numbers so we can keep track of how the algorithm works. Let's call them A and B, and we'll let A equal 11 and B equal 13. Now the receiver calculates the value of A times B. Let's call that answer C. In our case, C equals 11 times 13, which is 143. Then they find the least common multiple of A minus 1 and B minus 1 and call it D. Now A minus 1 is 11 minus 1, that's 10, and B minus 1 is 13 minus 1, that's 12. And if we think about the multiples of 10 and 12, the smallest one that's a multiple of 10 and a multiple of 12 is 60. So D equals 60. Now they choose another integer, let's call it E, where E is greater than 1 and co-prime with D. E being co-prime with D, sometimes called relatively prime or mutually prime, means that their highest common factor, or greatest common divisor, is 1. In other words, they have no factors in common apart from 1. Now, D equals 60 in our case, but would usually be a very large number, so we might have lots of options for a value of E, and generally larger values would make it harder for hackers to crack the code. But let's keep it simple and say our receiver picks an E value of 7. 7 has two factors, 1 and 7, and 60 has 12 factors, 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. The highest number that's in both of those factor lists is 1, so 7 and 60 are co-prime. Our E value is OK. Now the receiver chooses another integer, let's call it F, so that EF is congruent to 1 mod D. Now this means that there are a family of positive integer values of F that when we divide the result of E times F by D, we get a remainder of 1. The receiver just needs to pick the smallest F in the family. In this case, we've got E is equal to 7 and D is equal to 60. So we're looking for a value of F that means 7 times F divided by 60 is something remainder 1. Well, 61 divided by 60 is 1 remainder 1, so maybe EF is equal to 61. That would mean that 7F is equal to 61 and F is equal to 61 over 7, or 8 and 5/7. But that's not an integer. Or maybe EF equals 121, as 121 divided by 60 is 2 remainder 1. Then 7f would be equal to 121, and f would be 121 over 7, or 17 and 2/7. But again, that's not an integer. We can try other values for EF to give a remainder of 1 when divided by 60, 181, 241, 301, etc. And when EF equals 301, 301 divided by 60 is 5 remainder 1. Then 7f is 301 and f is 301 over 7, which is exactly 43. So we've got f equals 43. The receiver is now all set. They publish their public keys, C equals 143 and E equals 7, and they keep the other values secret, A equals 11, B equals 13, and F equals 43. Now the sender wants to encrypt the message 19 and send it to the receiver. If this were the decimal value of a Unicode character, it would represent device control 3, which isn't even a letter of the alphabet, so maybe it's not a great example, but let's not worry about that for now. We're just looking at how the algorithm works. Well, maybe 19 represents a house number rather than a letter. Rather than sending the number 19 though, which a hacker might be able to see, the sender calculates the value of 19 to the power of E mod C and sends that instead. So that's 19 to the power of 7 mod 143. Well, 19 to the power of 7 equals 893,871,739. So we need to calculate 893,871,739 mod 143. And that's the remainder we get when we divide 893,871,739 by 143. Well, 893,871,739 is equal to 143 times 6,250,851 plus 46. So the remainder is 46. So the sender sends the number 46 to the receiver. Now the receiver can decrypt this message by calculating the value of the message number received to the power of F mod C. So that's 46 to the power of 43 mod 143. But if you try working out 46 to the power of 43 on your calculator, you'll probably get an answer like 3.152004017 times 10 to the power of 71. That's 31520004017 with 62 zeros after it. But more importantly, it's wrong. Your calculator only keeps track of 10 or 12 significant digits, and that's not accurate enough for us to be able to decrypt our message. We need the full, exact value. Luckily, we can do a bit of clever maths to help us decrypt the message. We know that 46 to the power of 43 means 46 written down 43 times with a multiplication sign placed between each of them. We can express this in different parts that our calculator can handle more easily, and we can find the accurate remainder for each part. Our calculator can handle 46 to the power of 5. It's 205,962,976. So for example, we could use 46 to the power of 43 is equal to 46 to the power of 5, all to the power of 8, times 46 to the power of 3. And 46 to the power of 5 then equals 143 times 1,440,300 plus 76, which means that 46 to the power of 5 is congruent to 76 mod 143. And we can replace the 46 to the power of 5 with 76. And this means that 46 to the power of 43 is congruent to 76 to the power of 8 times 46 to the power of 3 mod 143. But 76 to the power of 8 is again too large for my calculator, so we can write it as 76 to the power of 4 all to the power of 2. And 76 to the power of 4 is 33,362,176, which is 143 times 233,301 plus 133. So 76 to the power of 4 divided by 143 has a remainder of 133. And similarly, 46 to the power of 3 divided by 143 has a remainder of 96. And substituting these back in, we can see that 46 to the power of 43 is congruent to 133 squared times 96 mod 143. And 133 squared times 96 is 1,698,144. But 1,698,144 is equal to 143 times 11,875 plus 19. So 46 to the power of 43 is congruent to 19 mod 143. In other words, 46 to the power of 43 divided by 143 has got a remainder of 19. The decrypted message is 19. Now, if that all seemed quite painful, just think about how much more painful it would have been if all the numbers were much larger. It's also worth thinking about how a hacker might try to intercept and decrypt the message. It would be relatively easy for them to intercept the encrypted message 46 and the receiver's public keys 143 and 7. However, without knowing the value of F, the hacker needs to work out what the values of A and B are in order to generate the values of F to unlock the code. In our case, with such a small C value, that would actually be very easy to do, but if it was hundreds of digits long, it would be really tough. Factorizing very large numbers is really difficult. So that's how it works. It's a brilliantly secure way to encrypt your messages so long as you choose very large prime numbers, yet the public key and the exact method used is available to everyone. Decoding messages encrypted in this way is just like trying to unmake a cake. But when large-scale quantum computers are developed, it might be quite a different story, as in theory, they'll be really good at finding factors of large numbers. But that's a topic for another video. When you subscribe to our channel, remember to click the bell to ensure you get notifications about our new videos. And for more mathematics content, why not follow the link in the description below to nagwa.com.